What if we shoot an arrow with a bow and we want to find the speed of that arrow after it is shot? So since the bowstring has been stretched, the force that it applies to the arrow is not constant as it returns to a stretched state. If you've ever stretched a cable or something stretchy, you might notice this. Even with the rubber band, you can tell the further you stretch it. We're going to talk about that more later, but as it stands, with a varying force that it applies to this bow, that force varies with the bow's position or with the, how stretched the string and the bowstring is, really. So it turns out that Newton's laws and our constant acceleration equations aren't enough to calculate the speed of the arrow at some later time. But our new concepts of work and kinetic energy, they are enough. We can solve these types of problems pretty easily, actually, because the work-energy theorem holds true even with varying forces. It also holds true when the body's path is not a straight one. So first, for a varying force, but straight line motion, I'm going to show you that the work-energy theorem is compatible with it. Say we have a particle moving along the x-axis with a force being applied to it whose x-component, Fx, changes as it travels along, like the bowstring on the arrow. Right? So there's some force here, and that's Fx. But it changes as the arrow moves, right? So say the force as a function of position along the x-axis looks something like what I'm about to draw. And it wouldn't exactly look like that. Well, I will do my best to draw as it would look for the bow, right? So it'd be it would look maybe something similar to this, but probably not something exactly like that. All right, so here, x1, and here, x2, this is in the x direction, and on the, this is the origin. On the y-axis, we have the force in the x direction. So the force as a function of position is basically what we're doing here. So this is F x2. This is F, here, Fx1. Right? Corresponds to that. That corresponds to where it starts up there. All right. So let's say that's the function, right? So to find the work done, we would multiply the x component of the force by the displacement along the x-axis. So in other words, we would find the area under the curve. All this area. Right? And that'd be easy enough if the force was constant, because this would be straight. And so it would just be finding the area of a box, right, with different lengths for edges. But now we have this changing function. So to find the work done, instead of just equals F dot S, right, which in other words would be force, the x component of force times delta x, right, x2 minus x1. But because it's not constant, then we apply the ideas of calculus, similar to what we've done in the past, and we take slices of this function. So if we wanted to find the area under here, it would be more accurate if we sliced this function up into slices, right? Even slices. And so that way, I guess I could have left this. That way, when we're finding the area underneath, we would find the area of these rectangular boxes, right? And add those up, and it would be much more accurate. And so maybe this is FAX, this is FBX, this is FCX, FDX, FEX. And this is delta XA, delta XB, delta XC, and so on. All right, make that bigger so you can see. Right? And of course, the smaller the width of those columns are that we're using to approximate it, the more accurate we get in finding the area under the curve, right? So what this translates to is, so if we used these columns, then we would be saying that the work is equal to the summation of all of these different things. So it would be FAX times delta XA plus FBX times delta XB, right? So we're taking the area of each of these columns and we're adding them up. And if we had the widths of these columns get skinnier and skinnier and skinnier, well then this gap part that's left out, which contributes to the inaccuracy of our area measurement, this gap part gets smaller and smaller and smaller the skinnier the width of these columns are. So if we take the limit as the width of these columns goes to 0, then we just have a bunch of essentially like infinitesimally small lines, right? Just an infinitude of columns. And then this gap that we have, that we're leaving out of the area, is so small, and if we're literally talking about the width of the columns being the limit as it goes to 0, then it becomes, we're not leaving out anything. And this is the language of calculus. And so, in that way, we have, well, here. We have a precise definition of work as being equal to the integral from x1 to x2 fx dx, right? So this would be the height of the column, and this would be the width of the column, dx being some infinitesimal width column. And the integral is you're adding them all up from x1 to x2. So this is work for a non-constant function. And now you might be able to see that, honestly, this is the true definition of work. And if the force is constant, if the force as a function of position is constant, then it's just a special case of this. So you can just write it a little bit more simply, like this, right? x2 minus x1, which is just fx delta x, or fxs, right? Or fs. So we get back to what we started with when we were just assuming a constant force. But if you have a non-constant force, if you have a varying force, then you have to consider this integral, and you have to be given the function of the force as a function of position. All right, so I'll grab my notes, which have flown out into infinity here. Got kind of off kilter there somehow. All right. How about the work energy theorem with a non-constant force and straight line motion? So I can derive the work energy theorem again for you, this time not assuming that the force is constant. Last time we were assuming a constant force. This time I can do it without assuming that and see if it's compatible, or prove to you that it is compatible. So first, note that from the chain rule, right, if we have AX is equal to dVx dt, right, that can be written dVx dx dx dt, right, which can be written Vx dVx dx. All right. So now, from our integral form of work total is equal to the integral of x1 from x1 to x2 of fx dx, right? And if this is force, then that can be written the integral x1 x2 to ma dx, and that's in the x direction, so max dx, all right, which can be written, and this is going back to what we had said about the chain rule earlier, x1 x2 m vx dvx dx, and then dx at the end here from this guy, right? And so, with a little bit of don't tell the mathematicians, you can get to x1 x2 m v x dv x, which, if you do that integral, gets you to 1/2 mv squared mv2 squared minus 1/2 mv1 squared, which is the same thing. So that would be the difference in, so that's k2, right? 1/2 mv squared, k2, minus k1 work total. And that's the work energy theorem. So there we did it. We did not assume a constant force. We got back to the work energy theorem. So that should prove to you that the work energy theorem is compatible for non-constant forces. Pretty cool. All right, so now I can show work energy theorem for motion along a curve. So what if you had a curved path? Does the work energy theorem apply then? Sure it does. I'll show you. So you have this curved path here. It doesn't have to be perfect circular motion like we've mentioned in the past. It's just some curved path. This is, we'll call this point 1, point 2. Yeah. And you have some particle here, I guess, right? Particle, we'll just say it's right there. And you have some force that's being applied to it. And it's going to be this way. So the component this way, remember we've talked about this in the past, this component is the one that is making it curve. And then since it's ahead here instead of behind, it's ahead, so that means it's actually speeding up along this path. Doesn't have to be, but that's the way we made it. But anyways, so it has some curved path. This would be, try my best to do tangent to this. That's pretty good. Alright, so it's tangent to that. So then that there would be some angle that the force vector is to the tangent. And there's some displacement from there to there, but we're going to say it's infinitesimally small, right? So you can section this off in various ways. We can take large chunks like this, right? Or we can take smaller chunks, and we can keep taking smaller and smaller and smaller and smaller chunks until we have chunks where the width of the chunk is, or the segment is the limit as the width of the segment goes to 0. And so we're going to call this, I'll use another color, we're going to call it DL. DL, I'll do cursive. DL. Alright, so during an infinitesimal displacement dl, the force F does work dw on the particle. So dw is equal to F dot dl, right? Which of course is equal to F L cosine the angle between them. All right. So it's only the component of force parallel to the displacement that does this, so that contributes to the work. And so this has some component this way and some component that way, right? And so this is F, we'll just call it parallel. F parallel, because it's parallel to the direction of motion along that DL segment, right? And so F parallel is equal to F cosine theta. All right, so hopefully you follow along with where I'm at with that now. I'm just going to leave it up here. So, like I said, the work done on each little segment, dw, is equal to F dot dl. And so then the total work done is this integral of all the segments. I'll keep that same color. There we go. Is the integral, so the total work is the integral from P1, point 1 to point 2 on our path, right? S F cosine theta dl, right? Which is equal to the integral from P1 to P2 of F parallel, right? The component of force that's in the parallel direction to the path, dl, which is the integral P1 to P2 of F dot, or scalar multiplied by dl. So what did we do? It seems kind of circular, but what did we do here? The force F is constant over any infinitesimal segment dl of the path. That is the key concept. So if we come back to our little picture here, the force might be changing as we're going along our path. It might be changing, right? But along every little tiny dl segment, if it's infinitesimally small, the force is not changing within that infinitesimally small segment, it can't. It's infinitesimally small. So during each segment, the force is constant. And so in that way, it's automatically consistent with the work energy theorem. Also, along each path, the force or the direction of motion is not changing direction. If it's infinitesimally small, then it's not changing direction. You can't have a curve because a curve implies that there's some path, right? But the path is infinitesimally small. So even if you have some really curvy path, if you just look at an infinitesimally small slice, because that's really what we're looking at, is just slices, the slice is straight. No matter where you look at the slice is heading straight. There's no width to analyze a curve within. And so if you think about that infinitesimally small segment concept, then you arrive at the work energy theorem being consistent with both a curved path and a varying force for the same reason. Because we're looking at infinitesimal segments and adding them all up. And in that infinitesimal segment, the force is constant and the path is straight. So it's automatically consistent. All right. So next we're going to talk about power. And that ends it for this video. So if you're not satisfied with this proof, just thinking about this infinitesimally small segment, I assure you that it could be proved more rigorously, but that's not something that we need to do. I guess I wrote that in my notes just in case any of you were furrowing your brows and thinking that I'm kind of waving my hands at this concept. But I just don't think that we need to get into any more complicated proof of this. We've done enough derivations and proofs for this lecture already. And I think that just conceptually helps you realize why it's true without maybe doing a rough or a rigorous mathematical proof. But if you're curious, I'm sure you can find it out there online. All right, that ends it for this video.